Welcome nocturnal minds back to our class. Oh, you are really study hard. Right, let's dive straight into the deep end. Philosophy of science isn't just some dusty old subject. It's fundamentally about wrestling with the big questions that pop up when we try to understand how science actually works. Think of it as the backstage pass to the scientific enterprise. We've got two main flavors here. The general kind, which tries to get a bird's eye view of what makes science tick as a whole, and then the specialized versions, which zoom in on the nitty-gritty within specific fields like physics or biology. So, what keeps these general philosophers of science up at night? Well, a whole bunch of fascinating puzzles. First off, the basics. What are we even trying to achieve with science? Is it just prediction, or is there something deeper? Like understanding why things happen, and how do we actually do it? Then there's the classic demarcation problem. What makes something science and not, say, astrology or creationism? How do we draw that line? We also grapple with the nature of scientific theories themselves. Are they mirrors reflecting reality or just useful tools? How do abstract concepts like force or gene connect to the messy world of observation? And what about the big ideas like causation, explanation, or probability? What do they really mean in a scientific context? Plus, how does science change? What triggers a paradigm shift? And don't forget the human element. Values, biases, social factors all play a role, right? These aren't just academic curiosities. They touch the very heart of how we know what we know. Now, while the general philosophy of science has been around forever, things really took off in the late 20th century. You saw a massive growth in the philosophies of individual sciences. Think about it. Quantum mechanics, relativity, evolutionary biology, these fields became so complex and internally rich that they demanded their own philosophical attention. It wasn't enough anymore to just talk about science in the abstract. People started digging into the specifics. What does non-locality really mean in quantum mechanics? What is space-time in general relativity? How do we define species in evolutionary biology? This shift was partly because the old, simple-minded ideas about science being a neat hierarchy, with physics at the top, just didn't hold water anymore. The focus moved from looking at the grand structure of all science to examining the intricate details within each discipline. But here's the kicker. Even as we zoomed in, the feeling persisted that science, despite its diversity, is still one coherent enterprise. So the quest for a unified understanding, even if we acknowledge the microstructures, remains a central, almost unshakable concern for philosophers. Let's rewind way back to the beginning. The ancient Greeks, especially Aristotle, were huge on this idea of episteme. Think of it as privileged knowledge, the kind that's solid, reliable, unlike mere opinion. For Aristotle, science was the gold standard, his model. It was beautifully structured, like Euclidean geometry. Imagine a system built on fundamental, self-evident first principles. These were about the essences or forms of things. How did you get these principles? Not through experiments, mind you, but through careful observation and what he called induction, basically, spotting the universal pattern in particular instances. From these first principles, you could deduce everything else, explaining why things behave the way they do. It was a deductive, causal explanation machine. Crucially, Aristotle saw this as both realist. These principles described the real natures of things, and empiricist, grounded in our experience of the world. Biology was his prime example of this ideal scientific form. But hold on, Aristotelian science hit a major snag. Try explaining projectile motion or why objects fall faster as they go down, using simple qualitative rules like heavy things fall towards the center. It just didn't work. The heavens' supposedly perfect circles didn't quite match the messy reality of planetary motion either. Astronomers, starting with Ptolemy, started building incredibly complex mathematical models that fit the data better, even if they felt a bit like fudging the underlying reality. Some clung to Aristotle's essence-based view, others basically gave up on realism for astronomy. Then came Galileo and Descartes, shaking things up further. Galileo famously said, "Nature's book is written in the language of mathematics." Big step. But he also realized that just describing the math wasn't the same as understanding the physical cause. When he tested his law of falling bodies, he deliberately avoided asking why they accelerate. Enter Newton. With his famous hypotheses, non fingo I fein, no hypotheses, Newton slammed the door shut on metaphysical explanations for phenomena like gravity. Science for Newton was about finding testable laws governing observable quantities. Forget digging into the ultimate causes or the microstructure of matter. That was beyond the scope of legitimate science. Newton's friend John Locke shared some of this skepticism, especially about getting at the real essences of things, the hidden inner workings. He figured our senses just weren't good enough for that. So natural philosophy, dealing with the unobservable, couldn't ever be truly certain knowledge, only probable belief. But then came David Hume, and he really threw a wrench in the works. Hume argued that all our beliefs about cause and effect, everything we think we know about how the world works, come from experience. Specifically from noticing patterns. A always happens before B, so A causes B. But here's the bombshell. How do we justify induction itself? How do we know that, just because the sun has risen every morning, it will rise tomorrow? Hume showed that any attempt to prove induction is reliable. Using experience is circular. It's like saying, I know induction works because past inductions worked. It just begs the question. So Hume basically said, forget trying to find a rational foundation for Newtonian science like the old rationalists wanted. The best we can do is describe how we make causal inferences based on habit and custom. Some see Hume as the first naturalist philosopher of science, focusing on how science is actually done, not just how it ought to be. Hume's skepticism left a huge gap. Scientists were incredibly confident in Newton's laws, applying them universally, treating them as necessary truths. How could that be reconciled with Hume's doubts about induction? Enter Immanuel Kant. Kant was struck by this tension. He proposed a radical idea. Maybe knowledge isn't just passively received from experience, nor is it purely innate. Instead, our minds actively shape experience through innate structures, categories like causality and substance, and forms like space and time. According to Kant, there are synthetic, a priori truths, principles that are necessary and universal, yet somehow derived from the structure of our own understanding rather than solely from experience. These principles, he argued, are the bedrock of empirical science. Think of them as the rules of the game we impose on the world. However, Kant's attempt to blend rationalism and empiricism faced its own challenges later on, particularly with the discovery of non-Euclidean geometries and the revolutionary theories of relativity and quantum mechanics, which seemed to shake the very foundations of classical physics, and by extension, Kant's framework. The 20th century really marked the coming of age for philosophy of science as a distinct discipline. It got its own departments, journals, the whole professional shebang. A lot of this was driven by scientists themselves who were deeply involved in the theoretical upheavals of the time. Think atomism, the weirdness of quantum mechanics, the bending of space-time in relativity. They weren't just doing science. They were questioning what science meant. They needed to understand the structure of their theories, the role of hypotheses and experiments, the justification for concepts like energy or field, and the limits of what counts as explanation. Names like Duhem, Poincaré, Boltzmann, Einstein, Mach, Planck, these weren't just physicists or mathematicians. They were also philosophers grappling with the implications of their work. This period saw the rise of various isms: realism, instrumentalism, conventionalism, positivism, each offering a different lens through which to view the evolving landscape of science. Then came the Vienna Circle and the logical positivists. Armed with the new logic of Frege and Russell, and Hilbert's formalism in math, they had a grand plan. Make philosophy rigorous, almost scientific, their weapon, formal analysis. They believed they could dissolve traditional philosophical problems, especially metaphysics, by showing they were meaningless because they couldn't be verified. Their famous criterion, a statement is only cognitively significant if it's either analytic,
true by definition,
like bachelors are unmarried, or empirically verifiable. This led to a sharp division: the logical structure of science, the justification context, versus the messy process of discovery, the discovery context. Philosophy of science became largely the logic of science, analyzing the syntax and semantics of scientific language. Think Carnap trying to build an inductive logic, or Hempel formulating his famous deductive nomological model of explanation. Even Karl Popper, with his falsificationism, fit into this mold, rejecting inductivism and psychologism. Before the 1960s, the dominant vibe was anti-psychologism, rejecting psychology of science, anti-historicism, ignoring history of science, and anti-naturalism. Philosophy is separate from science. But this neat positivist picture started cracking. Three big hitters challenged the status quo. First, W.V. Quine. He famously dismantled the analytic-synthetic distinction. If nothing is truly a priori, then maybe nothing is immune from revision by experience. This blurred the lines between rational and factual, and brought back naturalism. Philosophy isn't separate from science, it's continuous with it, using similar methods. However, Quine seemed less interested in how scientists actually choose between theories or revise components, and he largely ignored the idea that some principles might have a special, framework-setting role, what some call relativized a priori. Second, Wilfrid Sellars. He fought against instrumentalism, the idea that theories are just tools for prediction, arguing instead for scientific realism. Unobservables, he claimed, are indispensable for explanation. He also attacked the idea of a foundationalist epistemology, the myth of the given. Third, Thomas Kuhn. He threw down the gauntlet to philosophers who ignored history. He argued that understanding science requires studying its actual history, not just idealized rational reconstructions. Theory change isn't rule-governed, it's messy, involving values. Interestingly, all three thinkers drew inspiration from American pragmatism, its dislike of sharp distinctions and its focus on practical experience. These critiques paved the way for a major shift after the 1960s, the naturalist turn. Suddenly, psychologism, naturalism, and historical studies gained prominence. The idea took hold that findings from the empirical sciences themselves could be relevant, maybe even decisive, for answering philosophical questions about science. One exciting strand uses cognitive science to investigate how our minds represent the world through scientific theories, how theories connect to experience, and how scientific concepts develop. Another big area is the sociology of science, treating scientific practice as a social activity worthy of empirical study. But perhaps the most profound impact of naturalism is on how we justify scientific methodology. Naturalists argue that methodology itself is an empirical discipline. Scientific norms aren't discovered through a priori reflection. They're hypothetical imperatives. They tell us how to achieve certain aims, and their justification lies in their proven effectiveness in achieving those aims. It's a pragmatic bottom-up approach. Another big theme that shifted dramatically is the unity versus disunity of science debate. Back in the 30s and 40s, the logical empiricists were all about unity. Driven by empiricism, they aimed for a grand reduction, reduce the language of chemistry, biology, psychology, all special sciences to the language of physics, and then reduce physics itself to basic statements about observable things. Everything should ultimately be reducible. But by the 80s, the tide turned towards disunity. Physicalism, the idea that physics describes the fundamental building blocks of reality, remained popular. However, the incredible success and explanatory power of the special sciences couldn't be ignored. Why should psychology or biology just be reducible to physics if they have their own robust laws and explanatory domains? Philosophers like Jerry Fodor championed non-reductive physicalism. The idea is, just because physics is fundamental, doesn't mean everything else is reducible. Special sciences have their own legitimate laws connecting their own kinds of entities, and these play an essential role in explanation. It's like saying, physics provides the ultimate ingredients, but biology and chemistry tell us how to cook with them in ways physics alone doesn't capture. And speaking of metaphysics, it made a surprising comeback. After being largely dismissed by the positivists as meaningless, metaphysics regained relevance. The renaissance of scientific realism in the 60s encouraged optimism about science's ability to grasp truth. Then, by the 80s, philosophers started pushing back against the purely Humean view of causation and laws, the idea that causation is just regular succession and laws are just contingent cosmic habits. Non-Humean accounts, emphasizing necessity and proper laws, gained ground. This revival of essentialism and belief in necessity in nature brought metaphysics back into the philosophical fold. At the same time, a new formal approach gained huge influence, Bayesianism. Using probability theory, Bayesianism aims to provide a unified framework for analyzing concepts like rationality, confirmation, and inference. While some see it as just another attempt at a topic-neutral formal method, it's undeniably a powerful tool reshaping discussions in philosophy of science. So, as you can see, philosophy of science is far from a static field. It's dynamic, constantly shifting with old ideas, resurfacing and new ones emerging. Its value isn't just theoretical. It sheds light on the entire scientific enterprise, from the big picture down to the specifics of individual disciplines, even newer ones like cognitive science or climate science. And increasingly, it's turning its gaze inward, examining its own history and the intellectual battles fought over the decades. The companion volume we're drawing from reflects this vibrancy, covering the core issues across 4 parts, setting the historical and philosophical stage, exploring key debates, dissecting crucial concepts, and surveying the landscape within specific sciences. Alright, let's zoom into part 1 of that companion volume, which deals with the historical and philosophical context. We start with Chapter 1, focusing on conventionalism. This chapter, by Robert Dysel, dives into a fascinating doctrine: the idea that some core scientific principles aren't determined purely by evidence, but are chosen conventionally by the scientific community. It's a concept with deep roots and significant implications. So, what exactly is conventionalism in this context? The basic idea is pretty straightforward. Some scientific principles, particularly the deep theoretical ones, aren't settled by evidence alone. Choosing them involves a kind of conventional decision-making by the scientific community. Think about units of measurement: Celsius versus Fahrenheit. Is one system truer than the other? No, it's just a choice based on convenience. That's a clear example. But conventionalism pushes deeper. It suggests that maybe even the theoretical description of the world itself relies on such conventional choices. Where does this idea come from? A big source is the problem of underdetermination. The fact that any finite amount of evidence could, in principle, be compatible with multiple competing theories. If that's true, then choosing one theory over another involves a decision, a convention. This immediately raises big questions, especially for scientific realism. If empirically equivalent alternatives are possible, how can we be sure our chosen theory is the one that's objectively closer to reality? To really grasp the historical weight of conventionalism, we need to look back at the mid-19th century, specifically, the debates around the foundations of geometry and physics. Kant had this idea that geometry was synthetic a priori knowledge, meaning it was necessary and universal, yet somehow derived from our intuition of space. This seemed pretty solid until non-Euclidean geometries popped up. If you can have consistent mathematical systems that aren't Euclidean, could they also be descriptions of our space? Hermann von Helmholtz made a crucial insight here. He argued that visualizing non-Euclidean space isn't impossible if you can visualize Euclidean space. More importantly, he pointed out that our very concepts of geometry, like congruence and straight lines, rely on physical assumptions. We assume rigid bodies can be moved without changing size, and light travels in straight lines. This led to geometric empiricism, the idea that geometry studies the structure of space as revealed by physical measurements. Our belief in Euclidean geometry, Helmholtz suggested, is just based on the contingent fact that measurements using rigid instruments seem to confirm it. If measurements showed otherwise, we'd have to reconsider. Henri Poincaré took Helmholtz's empiricism and ran with it, taking a crucial step towards conventionalism. He realized that principles like light travels in straight lines or rigid bodies move freely without deformation aren't fundamental laws of nature that we discover empirically. Instead, they are definitions. They are conventions we adopt to give empirical meaning to our geometric concepts. Think about it. If we measure a large triangle and find its angles don't add up to 180 degrees, do we conclude space is non-Euclidean? Or do we say, well, we defined straight line as the path light takes, and according to our definition of Euclidean geometry, that path should be straight, so clearly light isn't traveling straight here? Poincaré argued both interpretations are possible. The choice between them is a convention. This means the truth question becomes secondary. It's about choosing the most convenient or fruitful framework. This idea profoundly influenced how we see the relationship between mathematics and physics, suggesting that axioms in physics, like F equals ma, might also be definitions in disguise, defining concepts like force and mass based on their empirical behavior. Poincaré's conventionalism wasn't just armchair philosophy. It played a real role in the scientific revolutions of the early 20th century, particularly in Einstein's work. Einstein explicitly used a similar reasoning. In special relativity, he redefined simultaneity how? By stipulating that the speed of light is constant in all frames and defining simultaneity based on that stipulation. It wasn't an empirical discovery about light. It was a definition designed to resolve puzzles like the Michelson-Morley experiment. Similarly, in general relativity, he redefined inertial motion as free fall and gravity as space-time curvature. When faced with evidence that contradicted Newtonian ideas, Einstein didn't just tweak the details. He changed the fundamental definitions. The logical empiricists like Schlick and Reichenbach embraced this. They saw the choice between Newtonian mechanics and relativity not as a purely empirical one, but as a pragmatic choice between different frameworks, each with its own set of coordinating definitions, linking theory to observation. They refined Poincaré's idea, arguing that scientists choose the simplest combination of geometry and physics, not necessarily the simplest geometry alone. Now, how does this relate to W.V. Quine's famous critique? Quine argued against a sharp distinction between facts and conventions. He pictured knowledge as a web of belief, where experience only touches the edges, and any part of the web can be revised if needed. For Quine, the difference between a convention and a hypothesis was just a matter of degree, not kind. This sounds like Duhame's holism, but Duham actually leaned closer to Poincaré, acknowledging that some principles guide inquiry and can be abandoned if the whole program fails. Poincaré himself wouldn't have called conventions true come what may. He saw them as establishing the framework within which we make truth claims. They connect our mathematical theories to physical reality, making physics possible. They are guided by experience and abandoned if they become impractical. Quine's web metaphor, while influential, arguably missed this crucial aspect: the way conventions act as bridges between formalism and empirical content, as vividly illustrated by Einstein's definitions, which were directly tied to empirical conditions like the constancy of light speed. So, wrapping up on conventionalism, it's important to remember it's not about arbitrary voluntarism. It's not about deciding something is true just because we want it to be. Rather, it highlights the crucial role of certain principles in giving meaning to our scientific concepts and connecting our mathematical theories to the physical world. It's about understanding the conceptual architecture of science, a point that, as de Salle argues, is sometimes overlooked in broader critiques. It remains a vital piece of the puzzle in understanding how science functions.